So our next talk will be lifting layers, analysis and applications.
Okay, good morning. My name is Meinhardt from TU Munich, and I want to present Lifting Layers, a collaboration with Peter Ochs, Leal-TaixÄ, and Michael Moeller. So first I want to start with a small motivation and why we need lifting layers as a new deep learning building block. Given some examples of an unknown function, in this case a sign, where we have x as a data point and f of x as a label, we want to somehow interpolate this function. A classical approach would be something like a linear spline. A linear spline is defined by knots and weights, and the number of knots is here defined as L. So let's just recap what a linear spline is. A linear spline basically tries to interpolate between those data points, and when we have in the data point x, we find the interpolation between the two different knots with those formulations. You can see that the interpolation coefficient lambda, if you put it back into the equation, actually leads to the data point x. Now, given the weights theta I and theta I plus 1, we can actually find an interpolation function of given those data points by the big F with the parameters theta. You can see that this whole formulation is still convex, and if we optimize this with a convex loss, we actually optimize a convex problem. This works pretty well for those data points. Now, looking at a more modern approach, something like a deep learning approach, we would, for instance, define a multi-layer perceptron. A multi-layer perceptron usually has multiple layers. We have a hidden layer, which is a linear layer, followed by some kind of activation function, in this case a rectified linear unit. And we would also try to put in our data points and try to optimize this model and try to fit our data points. However, due to the rectified linear unit, even though this is a very simple, low-dimensional problem, we would actually end up having a non-convex problem. The question is, can we somehow do better? Because if we optimize this, we would get something like this. In the beginning, the model would have had a hard time. After 75 epochs training on our sample data, we still haven't achieved any form of convergency, and only for an excessive amount of epochs we can actually find an optimal solution with this kind of architecture. Now, the layer that we want to introduce, which can be also integrated into a deep neural network, actually solves a non-convex or solves a convex problem, which is definitely a problem for the rectified linear unit, which in this case doesn't solve a non-convex problem, and it will actually preserve the data over the entire input interval. And by introducing this layer, this lifting layer, we actually achieve a way better optimization after only 75 epochs. So how does this lifting layer, which is kind of inspired by functional lifting, look like? So given a scalar input, we activate our neuron by lifting our value into a higher dimension of R up to the power of L in an Euclidean base. So if we remember the convex combination of our x between two different knots and the interpolation coefficient lambda, we actually try to lift our input value x to a higher dimension by just replacing the individual knots with the base vectors of our Euclidean base. For a simple example, this can look something like this. So we have our x, which here lies between T2 and T3, and is then a convex combination of the knots T2 and T3 with the lambda coefficient. And we lift this up into a higher dimensional space by replacing the individual knots and then actually getting a vectorized representation. So this has a lot of advantageous properties. So one is, for instance, if we combine our lifting layer with something like a linear layer, we actually show that this represents a linear spline. If we use this linear spline with a convex loss, we actually end up having a convex problem, and we can show that we actually find the best linear spline fit depending on our training data. Another advantageous property is that we actually still fulfill the universal approximation property so that we can approximate any continuous function, but in this case we don't need a hidden layer. Since we are actually optimizing a linear spline, we only need our lifting layer and the fully connected layer. And one big advantage with respect to rectified linear units is that we actually don't lose any input data. So all the different input intervals are lifted into different high-dimensional dimensions and are kept there. So we don't have the problem of vanishing gradient or dead ReLUs. And we have a non-zero gradient always, because there's always data preserved in one of the dimensions. And that's why, just to recap this result on this similar on this easy problem, our approach by having similar amount of parameters actually optimizes this low-dimensional easy problem in a convex fashion and optimizes it way faster and converges to an optimal solution in a way faster or with way less epochs. Now the question is, since we kind of closed the gap between low-dimensional interpolation problems to high-dimensional problems, or we're trying to close this gap, the question is, will this new deep learning building block also work for high-dimensional problems? High-dimensional problems for us is everything larger than, or with a dimensionality of larger than 1. One thing we will definitely lose is the convexity. So while for low-dimensional problems we still have the property of convexity for our problem, this holds not true for high-dimensional problems. And we will apply our scalar lifting component-wise. We also have a vector-valued lifting presented in the paper, but for here we also want to stick to the scalar lifting presented a few slides before. So for our high-dimensional network problems, we have this special case of our lifting, which is for 2 labels, and basically comes up to this, and we applied this to multiple high-dimensional neural network problems. One problem, for instance, is image classification. We applied this on MNIST and compared this lifting layer with different kind of activations. One is, for instance, ReLU, the other one is max out, which has a similar piecewise optimization strategy. And we show that our lifting layer actually converges better and converges to a lower test score on this similar example. A really high-dimensional deep learning problem was something like Gaussian image denoising, where we compared our approach to standard state-of-the-art approach, the DNCNNN, and we achieved a similar final score because there's a very special trick in the training scheme with this, where we drop the learning rate, but you can see that the overall convergence behavior is superior to the standard DNCNN. Without the learning rate drop, we actually achieve an overall better validation Pearson-R. Another extension to our approach is actually when you kind of not only lift the different the individual layers, but you can actually try to lift the output. So what we're doing here is basically we approximate a non-convex loss with a linear spline, and we then use the lifted output of the neural network, and we try to do the prediction of our problem in this lifted representation. This allows us to convexify non-convex losses. We showed this in the paper only for this truncated linear loss in a one-dimensional problem, but it's very, but the results seem very promising. Because since we, for instance, have when we have this interpolation problem in 1D, now with 40% outliers, you can see that for a regular convex loss, we achieve a suboptimal interpolation. If we optimize a truncated linear loss just by SGD, we also get a suboptimal interpolation. But if we use our lifting the output, so we lift this truncated linear loss, with, or we represent it by a linear spline, we use the lifted output of the network, we can actually achieve a close to optimal interpolation of our data points. This works pretty well for this truncated loss, but as I said, we have to further explore different neural network losses and how this actually works for deeper neural networks. So in our paper, Lifting Layers, we introduced a spline-like lifting as a nonlinear activation function, which has some, or which tries to unify the low-dimensional problems with high-dimensional problems. So basically, trying to close the gap where something like the ReLU fails. We achieve way better accuracies on, or way better interpolation properties on low-dimensional problems, but still achieve good results on high-dimensional problems. And this kind of gap it was missing with the ReLU activation. We introduced this new building block to basically, how can I say, that since we always multiply the number of parameters in the next layer by lifting this dimension, we're basically introducing a kind of new building block where we hope for new kind of architectures that might build upon on this and maybe change neural network architectures in general. Our code in MATLAB and Python is available on GitHub. Our poster session is on Wednesday, and we also have a workshop paper on Friday where we are happy to see you. Thank you very much. Are there any questions?
Thanks. Do we have any questions?
Okay, I may have a question. So you said you can lift up this loss function to make it convex. Is that right?
You mean the lifting the output part?
Yes.
Yes.
But then the network itself remains non-convex, right? So
Sorry?
The network itself that you're optimizing
Yes,
remains
the
non-convex.
lifting the output case is just for this one-dimensional, where we have only one final layer, basically. So in this case, we have our lifting layer and then one fully connected layer. And in that case, the entire network can be convex.
Okay.
Because it's not a deep neural network.
Right. Okay.
Yeah. So extending this to real deep neural networks, definitely one problem is that the network will not be convex. Yeah.
Okay. Any other question? Okay. If not, let's thank the speaker again.